Stable and stable equilibrium. Torque. Negative charges placed into the opposite side torque like this way. Okay. So, hello bacho. Sat Sri Akal and Namaste from my side. How are you all? So guys, this is Indrajit Singh. Right. Welcoming you all into the most sensible platform for an aspirants, those who are preparing for JEE NEET kind of examination. Hi everyone. Okay. So, what will be the agendas of the today's lecture? We are going to discuss this meme afterwards. What will be the agendas of today's lecture? Agenda of today's lecture. Electric dipole moment, right? Electric field is because of the electric dipole, torque, potential energy, and lots of things are there. Okay, lots of things are there. Okay, so it's a very simple thing. Lots of things are there. It's a very simple thing. Rhymes. Okay, so let's move all of this apart. So guys, I think today's lecture would be right awesome. As yesterday I told you all, we discussed the electric field is because of the point charge. We'll discuss the electric field is because of the continuous bodies and n number of the charges. In that part, in that classification, I told you all that one thing is remaining, that is electric field as because of the dipole. Electric field as because of the dipole. Now in that, multiple cases are there. General points are there, lots of things we need to discuss it. Okay, lots of the things, right, we have to discuss. Electric field is because of the dipole on the axial point, on the equatorial point, and the general point, and the formulations, their mathematical representation, what happens when the dipole is kept into the uniform electric field, how torque is evaluated, what happens when the dipole is kept into the non-uniform electric field, right, what kind of the qualitative decisions comes out, right, what kind of the quantitative decisions come out. Lots of things we are going to discuss. Okay, what is a stronger field, what is a weaker field, okay, and some of the examples based on to the previous sessions. Okay, so today is a Thursday. Okay, again my class will come up on the Monday, on where the maximum practice based question we are going to have. Okay, practice based question we are going to have it. Okay, so this happens when dipoles, right, okay, the torque, okay, what we can say, whenever the dipole moment is perpendicular to the electric field, okay, then torque is maximum. Torque is maximum generally like this way, and this is nothing else but in dipole. The positive and the negative charges separated by some distance d. Okay, electric dipole. Okay, so this was a fun part. As usual, I used to tell you all that our lecture starts with a small. Our lecture starts with the small. Okay. Okay. Electrostatic, right, in which the most important, right, question or the most important concept of electric dipole and its electric field. Okay, directly we are moving forward to the concept. First of all, what actual is the electric dipole? What actual is the electric dipole? Right, simple. See, basically I told you all we are having the two kind of the charges. The first one, that is a positive. The second one, it is a negative. Right, when the positive and the negative charges are separated by some distance, let's say L. Okay, this is a positive charge having magnitude Q, right? Okay, this is a negative charge, they are separated by some distance D. The entire system formation, right, this is known as electric dipole. the entire system formation, it is known as what? Electric dipole. Okay, the name itself states that two monopoles are combined. Okay, two monopoles are combined to form a dipole. Two monopoles are combined to form a dipole. Right. How the electric field is because of this dipole is calculated. Today's lecture is not going to be as much long as what we are expecting, 1 hour 30 minutes long, because electric field is because of the dipole is there. Okay, but so lots of easy derivations and lots of easy calculations are there. Okay, lots of easy derivations and the calculations are there. Okay, so we are going to enjoy a lot, because this lecture is going to be short, sweet and sober. Short, sweet and sober. Okay, now with this electric dipole, some of the noteworthy points are associated, right? Some of the noteworthy points, right? That is, first, electric dipole moment, that we are going to discuss it in a few minutes, right? Okay, some of the direction of dipole moment, right? Through this electric dipole, what happens to the net electric field at an axial point? What happens, right, to the net electric field at the equatorial point? Right? What happens to the net electric field at the general point? What happens to the net electric field? Okay, these are the 3 points. And the dipole in uniform electric field, dipole in non-uniform electric field. All of those things, right, we have discussed. And we are going to discuss. I'm extremely sorry for that, right? So first of all, what actual the dipole is all about, right? One positive charge, right? A system of the positive and negative charge. I'm extremely sorry. A system comprises positive and negative charge separated by distance L. Right? A system comprises positive and negative charge separated by the distance L. Okay, system comprises the positive and the negative charge separated by the distance L. Okay, so in this case, what happens, right? How we are going to define the each and every stuff, let's see. But first of all, the important thing is electric dipole moment. Okay. Because see, electric dipole is a system, but if you want to represent in terms of the entire thing, if you want to represent in terms of the physical quantity, then we need a dipole moment. Okay, so here comes the dipole moment. Positive charge, negative charge separated, right, by the distance L. Separated, I think it's not right visible. Separated by the distance L, right? Separated by the distance L. Now, what does this electric dipole moment states? Okay, electric dipole moment. Generally, we are not having any kind of the technical or any kind of the, what we can say, the definition that is having the grammatical formations. No. Simply in maximum number of the resources, the electric dipole moment is defined as, right, Q into the distance between the two monopoles, right? Q, charge on, or you can say magnitude of charge on each monopole, right? And second, the L is distance between the two monopoles. Right. Magnitude of the charge on the each monopole, right? L is the distance between the two monopoles. Okay, this is defined as the product of the magnitude of the charge on the each monopole and the distance between them is defined as dipole moment. Yes, electric dipole moment. This thing is going to this thing is going to contradict when we will right, understand the concept of magnetism, right? When we will understand the concept of magnetism, right? In magnetism, monopoles kind of things never exist, but we are not going to move on to that part. Okay, we'll discuss into the later. So if I want to compare the electric dipole, okay, into the day-to-day life, one girl and one boy, right? In another sense, you can say a married couple, right? One of the opposite nature, second of the opposite nature, right? Fell in love with respect to each other, right? Got married. Now, what happens? First month of the marriage, whoa! Second month of the marriage, see, at the first month of the marriage, see, the first, you can say the positive and the negative charge, right? They are separated by distance L. Into the first month of the marriage, wow, things are like heaven. Boom. Now, slowly, when they stay together with each other for the long amount of the time. Okay, now what happens here? Okay, now we are able to visualize all of those stuff. Some of the pros, some of the cons, some of the positive points, some of the negative points, some of the reactions, some of the behaviors, some of the weird reactions, some of the weird moments, some of the awesome moments. Right. So in that case, oh, now we are getting bored. So with the increasing amount of the time, the bond and affection, in some cases it increases to an extent, right? While the bond and the affection into the sum of the cases, it decreases to an extent. So here the electric dipole moment, right, the day-to-day life, the bonding between the couples, okay, generally, right, it is always from negative to positive charge. So bonding into a day-to-day life is generally from woman to man. Please don't mind, I heartily apologize for that, right? From negative to positive charge. Affection, the bond exists between the, the lady and the gentleman, okay? So generally, okay, the gentleman is busy, okay, into the financial matters, right? He is working and all. Even today, right, the woman empowerment is also on the peak, right? So they are working also high. So right now, if I'm talking about the present moment, right, if we are comparing this to the day-to-day life, then exactly we are not able to define the direction of the dipole moment. Generally, woman holds more affection as compared to boys. This is a study, this is a survey, right? So the dipole moment direction is always from negative woman to man, negative to positive direction, negative to positive direction. So here, if this is the dipole moment, right, this is the formula of the dipole moment, okay, the first important point that electric dipole moment is a vector quantity. Electric dipole moment is the vector quantity. Second, direction of dipole moment is from negative to the positive. Direction of the, so suppose if this is a dipole, then how we are going to define the direction of the dipole moment? If this is the dipole, how we are going to define? I think only the white pen will work. This will be the direction of dipole moment, right, from negative to the positive one, and it is denoted as P. Okay, the symbolic notation for the dipole moment is P, right? So P is equal to Q into L. Q is the magnitude of the charge on the this monopoles. L is the distance between the two monopoles. Being a vector quantity, it is having magnitude in the direction. Magnitude is represented by this. Direction always come up from negative to the positive charge. Okay, from negative to the positive charge. So this was all the entire detail regarding the electric dipole moment. Okay. Now, basis on this, we are going to see some of the formulas. As the electric dipole moment is the vector quantity. Okay, being a electric dipole as the vector quantity, it means the net or the resultant dipole moment of more than one dipoles is not going to be algebraically added. Is it possible that in entire system only single dipole is present? My question is to you all is it possible that in entire system no. Okay. Is it possible that in entire system only one? No. Then simply if we want to define what will be if more than one dipoles are present, then what do you want to tell about the resultant dipole moment of the system? Okay, simple. In a resultant dipole moment of the system, right? Okay, what happens? The individual dipole moments are vectorially added. Individual dipole moments are vectorially added. Okay. So suppose if the system is having more number of the dipoles moment, that P1 and P2. Let us take an example to understand this. Let's take an example of the hydrogen molecule, right? Okay, the bond formation into it, you've seen into the chemistry, right? The bond formation into it, O, H, this kind of the formation is there. Now this being a negative, this being two positives, right? Are we having any kind of the dipole moment within it? Yes, we are having the two dipole moments here, right? One being associated from the negative to the positive charge, second being associated from the again negative. So what will be the resultant? This is the bond angle theta. Generally, you have seen the value of the theta. Okay, this is a standard value. Right now, we are not moving into that part, but this is a standard value. But the thing that I want to convey in front of you all, okay, the thing that I want to convey in front of you all, this is the first dipole moment, this is the second, okay, then the net dipole moment will be the vector addition of the two individuals, okay, the net dipole moment will be the vector addition of the two individuals. The net dipole moment will be the vector addition of the two individuals, okay, vector addition of the two individuals, right? So here the net dipole moment, okay, the net dipole moment, okay. So this thing we are going to see into the example forms, right? And you are going to enjoy. The first step should be initial. Let's calculate the resultant dipole moment. Then we are going to see the electric field is because of the equatorial and axial point and the general point, and in the uniform and non-uniform electric field, lots of things, right? So now first, okay, example. Suppose I am having a system, right? This is the positive charge, this is the negative charge, right? And you are having, let's say these are the two positive charges and this is a, okay, these three charges are kept on the vertices of the equilateral triangle. Three charges are kept on vertices of equilateral triangle, right? Okay, What we need to calculate? We need to calculate the net dipole moment as because of it. The net dipole moment as because of it. Right? The net dipole moment as because of it. Right. So first of all, understand the individual. See what happens here. Okay, it is important. The step one. Okay, step one. It is important to understand how dipoles are formed from the monopoles. Right. The question, the solution relies behind how the dipoles are formed from the monopoles. If we are not able to calculate how dipoles are formed, then how you are going to calculate the net, the resultant dipole moment of the system? Suppose here the -2 charge is there. Can I separately write it as a negative of Q, negative of Q? Right. Okay. Quantization of the charge. Charge can be divided, but it should be into the whole number. The fraction of the charge is not possible. Okay. So I am dividing into the some specific value. It's not a fractional one. Okay, it is not a fractional one. Now what happens here? One dipole moment is formed here, and the second dipole moment is formed. One dipole moment, I am naming it as a P1. It is directed from the negative to the positive charge. Second dipole moment is directed from the negative to the positive charge. Angle between the two dipole moment, it is 60 degree because the triangle is equilateral triangle. Okay. The one dipole moment formed, that is P1. The second dipole moment formed is P2. The angle between the two dipole is 60 degree. Now here we are going to have the vector addition of it. To calculate the resultant dipole moment, okay, what we are going to do, we are going to vectorially add all of those stuff. That is P1 square, P2 square plus 2P1, P2 cos of 60. Now being charge on monopole is same. Charge on monopole is same. So what happens here? Right. So it's P square. Charge on the monopole is same, and being an equilateral triangle, on the vertices of the equilateral triangle, the distance is also same. So in that case, both of the dipole moment would be having the same magnitude. Both of the dipole moment would be having the same magnitude. So here it is P square plus 2P square cos of 60. Right. So the resultant dipole moment, it is going to come upon as root 3P. So that is equal to what? Root 3 P. P is like QL. Okay. So the resultant dipole moment of the system is root 3Q of L. This is how the dipole moment is calculated. Okay. This is how the dipole moment is calculated. In this kind of the thing, lots of formations we can have. Right. Lots of formations. Okay. Another formation, if I'm going to tell about, but it's okay. You can place it on the square. You can place it on the rectangle. Okay, on the four vertices, right? You can take any of the polygon and you can keep, right? Okay, but the more the number of the sides of the polygon, right? The more complexity you are going to feel while solving the sum, right? The more into the number of the sides of the polygon, the more into the complexity you are going to feel while moving on to that. Okay, so here, this is how the resultant dipole moment being in vector quantity, being having a direction, this is how the things are going to get evaluated. Okay. Now, basis on this one dipole moment, I'm going to give you all one example. Simple. It is asked, right? Calculate the net dipole moment of the system. net dipole moment of the H2O, right? So guys, this is a homework for you all. I want you all, right? This is actually some students are going to use their brain immediately. There you going to search on a Google and what will be the value of the net dipole moment of the H2O, okay? And they are going to write up the answer, sir, first answer. Please don't do like that, okay? H2O, the structure of it, you all are aware of. The bond angle between them, you all are aware of, okay? Take the first dipole, okay? Identify the two monopoles, okay? And identify onto the opposite side, right? Just try to figure it out, the direction of the dipole moment of each, okay? And then with using the bond angle, calculate the value and just check it out whether your value is matching up to the standard value or not. Okay, check it out, your value is matching up to the standard value or not. It is important, right? So this is a homework from my side. I will be waiting for all of your comments beneath the video regarding it. Okay, I will be waiting for all of your comments beneath the video regarding it. Now, let's move on to the next part. Okay, electric field is because of the dipole, right? Electric field is because of the dipole. Okay, I'm sorry, just hold on, I think. Okay, electric field is because of the dipole on the axial point, right? Electric field is because of the dipole on the axial point. Okay, I think let's take that stuff. If dipole is present into the three-dimensional space, okay, I'm talking about the line joining the two monopoles. What will be the value of the electric field, or how electric field variations are measured into that? How electric field variations are measured into that on moving on all of those points on the axis of the dipole. Moving on all of those points on the axis of the dipole. Right. Suppose this is a Cartesian coordinate system and this is an origin I am talking about. Here one positive charge is taken, here one negative charge is taken. What will be our agenda? To calculate the net electric field. See, this is a positive charge Q, this is a negative charge Q. They are separated by the distance L. Right, with respect to the origin. Okay, they are separated by the distance L with respect to origin. This distance can be anything. Generally, students are having the misconception that distance is always 2L. No, it's just a distance between the two. The definition of the electric dipole moment never tells you all, it never screams that all the time the distance between the two monopoles is going to be 2L. No, it's not true. It is based on the very simple fact that the distance is 2L. Right? Okay. So here what happens? What will be the agenda? We have to calculate the net electric field on, right, P as of dipole, right? Okay, as of dipole. So this is a point. Let us take an example. This is a point. Okay, this is a line that joins the two dipoles. This is a line that is joining the two monopoles, right? How the electric field variations are there, right, on the each point on the axis of the dipole. So for that we are going to select one specific point, right, that is at the distance y. Okay, through this we are going to obtain one equation, and through that equation we are going to analyze how the variations of the electric field happens, or how the electric field is varying. Okay, so here what happens? Q minus Q separated by the distance L. See, if I am talking about point P, just mark my words. If I am talking about the point P separately, I am writing here because I need a space to explain you all. As because of the positive charge, electric field is in this direction. As because of the positive charge, electric field is in this direction. As because of the positive charge, electric field is always in outward direction. As because of the negative charge, electric field is in this direction. So what will be the net electric field? Electric field is because of the positive charge, negative, as electric field is because of the negative charge. Electric field is because of the positive charge, negative electric field is because of the negative charge. So the distance between the point and the positive charge, can I say if this is L, then this is Y minus L. Distance between the point and the negative charge, Y plus L, right? Y plus L. So here what is going to happen? Field is because of the positive charge, that is KQ whole divided by, right, Y minus L whole square. KQ whole divided by Y plus L, right, whole square. Right now I'm taking it as a magnitude N, right? You can take it as a J also, but in general terms I'm defining it. Okay, in general terms I am defining that part. Okay, so the net electric field, that is defined as KQ, right, that is Y square plus L square minus 2LY, right? Okay, sorry, plus 2LY minus Y square minus L square plus 2LY whole divided by Y square minus L square whole square. So this is Y square L square, Y square L square is going to get cancelled. Okay, so what we are going to have, the net electric field, that is equal to KQ, right, into 4 of L Y whole divided by Y square minus L square whole to the power square. Okay. Now what happens here? The net electric field, into unit vector N. So the net electric field, if I am rearranging this term, then what happens? I can say it is 2kp, where p is a dipole moment of the system, right? 2kp into Y whole divided by Y square minus L square whole to the power square. Okay, this is a general formula, but okay, it happens if, right, if L is less than Y, right, if L is less than Y, right, then the net electric field, it is given as by the equation, right, that is equal to 2kp whole divided by Y cube into unit vector N. Okay, so this is the equation of the electric field as because of the dipole on the axial point. See how they are getting varied. Okay, how the equation is getting varied, just check it out. Okay, how the electric field, it is 2kp by Y cube. Okay, we can understand P is also having the dimension of a length, but here the electric field is inversely to the Y cube. Okay, the less the value of the Y, more will be the value of the electric field, higher will be the value of the Y, right, less will be there. So if we are nearer to the dipole, then the value of the electric field would be high, the intensity of the electric field would be high. If we are moving slowly away from the dipole, then the intensity of the electric field is less. Intensity of the electric field is less. Right. So this is the first term, electric field, right, as because of the dipole on the axial point. Now let's move on to the next. Electric field is because of the dipole on the equatorial point. Okay, we are going to, I think this thing has been misinterpreted. Okay, now let's move on. Okay, equatorial point. Okay, again we are going to take some example. This is a positive charge, right, this is a negative charge. The positive charge and the negative charge, they are separated by the distance L. What will be the agenda? What will be our agenda? Agenda is to calculate, right, the net electric field at the point P. Okay. Calculate the net electric field, right, at point P. The net electric field at the point P. That P is equatorial point to the dipole. P is the equatorial point to the dipole. Right? P is the equatorial point to the dipole. Now what happens here? Okay, see, I'm going to take this P point nearer because we need right, some space to evaluate. Okay, suppose this is P, this is L, this is a perpendicular distance R. As because of the positive charge at the point P, electric field will be directed outwards. Suppose if this is theta, then this is going to be E cos of theta and this is going to be E sin of theta. Right? We can resolve into the two components. This is theta, they both are vertically opposite angles. Right? Both are vertically opposite angles. Now what happens here? This is a negative charge. Electric field, as because of the negative charge, is directed in this way. Okay, so this is going to be E cos of theta and this is going to be E sin of theta. In all of those sense, the cos component will get cancelled. Cos component, the horizontal component of the vertical field, will be get cancelled. So whatever the net electric field it is going to come, it is only going to come as because of the vertical component, that is equal to negative of 2E sine of theta. Here you can take, and to the previous example we took as a unit vector n, but here we can take it as a j because it is right, directing into the negative j direction, into the negative j. Right? Yes or no, guys? Okay. So the net electric field is equal to negative of 2E sine theta into j. Now what happens here? Negative of 2E sine of theta into j. Okay. Can we replace? See here. It is RL. Can I say, according to the Pythagoras theorem, that is R square by L square. Okay. So this is going to be negative of 2KQ whole divided by R square plus L square, right? Sine of theta into j. Right? Sine of theta into j. Simply, if I am going to define this triangle, this is theta, right? This is R, this is L, this is under root of R square plus L square. R, L under root of R square plus L square, right? So what happens here? Okay, what happens here? If I am going to define the sine theta, then it is going to be L by under root of, so this is negative of 2KQ into L whole divided by R square plus R square, right, into L whole divided by R square plus L square whole to the power half. So this is going to be K into, negative K into 2QL whole divided by R square plus L square whole to the power 3 by 2. This will be the dipole moment, right? So the net electric field, it is going to come upon as negative of Kp whole divided by R square plus L square whole to the power 3 by 2 into J. Again, if we are going to discuss that, right, L is less than R. So the electric field is because of the right, equatorial point, it is negative of Kp whole divided by Rq into J. And generalized form, it is written as negative of Kp whole divided by R cube into unit vector n. Right, because dipole can be placed right, anywhere into the Cartesian coordinate system. So for as that purpose, the general point is needed. Right, as of that purpose, the general point is needed. Right. Okay. So this is an electric field into the dipole is because of the equator. Electric field, okay, of the dipole is because of the axial point, right? And electric field, like some of the examples I give show. Okay. Now let's move on to the electric field is because of the dipole and the general moment. Okay, so what happens here? What happens here? What happens here? Right, what happens here? Okay, see students, I'm having one complaint here. I'm saying, right, see, for us, if we are teaching upon the YouTube, okay, then your response and support from all of your sides is needed. It is indeed needed, right? If you are not replying or if you're not supporting us, then who is going to help? Yes, I will help this. This is for you all, okay? Many students were commenting that we need this kind of the batch, we need that kind of the batch. So for that of our reason, right, we were about to launch this batch live, okay? We were about to launch this batch live, okay? We were about, but here what happens, okay? We were having an thought that we should all give you the classroom experience, the regular coaching kind of the experience. So for as of that reason, right, we have kept this batch, right, excellence batch on the regular basis. Okay, please don't sit back, come forward and show us your support. Please don't sit back, come forward and show us your support. Right? Yes or no, guys? Come on, everyone, those who are live. Okay, we are in a need for your. Okay, so now let's move on to the electric field as because of the general point. Okay, when a dipole is quite small, there is a difference. Okay, there is the difference. Let us take an example. If this is a positive charge and negative charge, right, and they are separated by the distance L, right? They are separated by the distance L. See what happens here. If value of the small L is quite negligible, right? If value of the L is negligible, then it's a very simple stuff, right? Value of the small L is negligible, then the dipole is represented through the dipole moment. Dipole is represented through the dipole moment. Okay, dipole is represented to the right dipole moment. See what happens here. If we are talking about the short dipole, right, electric field due to the general point. Let's take an example what general point it can be. Suppose this is a dipole. This is a point P. Our agenda is to calculate the net electric field at the any point P. Okay, the net electric field at the general point P. Right, electric right field, net electric field at the general point P. Okay, so what happens here? Okay, net electric field at the general point P. Okay, so now suppose this is the point P, this is a dipole and this is at the angle theta. This is point P, this is dipole and it is at the angle theta. As because of this dipole we need to calculate the net electric field at the general point P. See, this dipole comprises, if I am moving upon, this will be P sine of theta. And this will be P cos of theta. As because of this dipole, on the equatorial point, we will be having, this will be the axial point, right? Okay, if I'm talking about the point P, this is a dipole, right? At any general point, electric field at any general point will be the vector addition of the electric field at the axial point and the equatorial point. Okay, so this is an axial point, this comes electric field at the equatorial point. The resultant of this two will give the net electric field at the point P at any general point making angle phi with respect to the dipole, right? One of the components of the dipole, right? So this is the general explanation I'm talking about. Okay, this is the general explanation. See, this is this in some of the resources, right? This might be having the long of the explanation. Okay, but right now we are just summarizing into the net electric field at any general point, that is 2 kp whole divided by y cube right, into I plus Kp by y cube into J, right? But this is associated with the one of the components of the dipole moment P cos theta, and this is associated with the one of the components, right, that is P sin theta, right? So actually we can't like this way, we can't write it down like this way, okay? Okay, we have to write that stuff like the net electric field, okay, at any general point, it is 2 Kp cos of theta whole divided by y of cube into I, right, plus Kp sine of theta whole divided by, right, y of cube, right, into J. Okay, this P, the dipole moment that is associated with an axial field is P cos theta. The dipole moment that is associated with the, right, equatorial, that is P sine of theta. So resolving this, you are going to get the two most important results, right, and those are quite important from the JEE mains point of view and the advanced point of view, right? So the net electric field in terms of magnitude, that is going to come upon as Kp by y cube under root of 1 plus 3 cos square theta into unit vector n, right? Okay, here it can be Ij, right? It's okay, but right now I'm just telling up, okay, let's not waste the time and write down the magnitude, okay, because we have done all of those stuff, that's why. Okay, so this is the right magnitude of the electric field at that specific point. Okay, now there exists the relation between this phi and theta. There exists a relation between the phi and theta. How we are going to identify this stuff? Let's see. Okay, see, if I'm talking about the tan phi, then it is y component by x component, right? So it is Kp by y cube sine of theta whole divided by 2 Kp by y cube cos of theta. This is going to get cancelled, right? So we are going to get the new result tan of phi, that is equal to half tan of theta. Okay, tan of phi, that is equal to half tan of theta. So this is how the electric field is because of the general point it is defined. Okay, electric field is because of the general point it is defined. Its respective equation that holds in quite importance, right, and its angle. Okay, and its angle, right or no? Yes or no? Okay, now let's move on to the next part. What happens when dipole is kept into the, see here, before this, if I'm talking about the electric field, then all of those electric field part is covered up. We have seen electric field is because of the point charge, its general definition, right? Electric field is because of its vector form. Electric field is because of the n number of the charges at any point into the Cartesian coordinate system. Electric field is because of the continuous bodies like the finite length wire, infinite length wire, ring on its axis, its maximum value, right, its minimum value, its respective graph, right, the finite plane, finite charge disk, infinite plane, everything we have seen that part. Everything we have seen. Right. So from now, electric field is because of the dipole, electric field is because of the right at the axial point, at the equatorial point, at the general point, everything we have seen. Now it's time. So here the electric field equations get over. Electric field equations gets over. So now here electric field into the when what happens when the dipole is kept into the uniform electric field? See, it's a very simple concept. When it is kept into the uniform electric field and when it is kept into the non-uniform electric field, all of those assumptions you are going to do on the basis of net force and net torque. Okay, how dipole will react in external field how dipole will react in external field completely depends on, right, the two most important right points, that is the net torque, okay, and net force. If I am talking about, generally this concept is discussed after electric field lines, right? But electric field lines I have kept separately for the Gauss law, right? Electric field lines I have kept separate, right, for the Gauss law. Okay, so here, electric dipole into the uniform electric field. How we are going to judge this out, right? Okay, suppose field is uniform, electric field lines are parallel and at the equidistance with respect to each other, dipole is kept. Just keep one thing into the mind. The positive charge always moves into the direction of the field. Positive charge moves always into the direction of the field. Negative charge moves in opposite direction to the field. Suppose when dipole is kept, what happens here? When dipole is kept, this is the positive charge. The direction of the electric field is in from left to right. The direction of the electric field is from left to right. So obviously this positive charge is going to be, right, move into the direction of the electric field. So this positive charge will experience whenever the dipole that is separated by the distance, right, 12, it is kept in an external magnet electric field. The positive charge will, right, feel the force in this direction, right? The negative charge will feel the force into the opposite direction. Positive charge will feel the force, right, okay, into the direction of the field. Negative charge will feel the force into the opposite direction of the field. So here, if I'm talking about the net force, right, so that is equal to F1 minus F2, being an electric field is constant, right, as a constant. So can I say it is QE minus QE is equal to 0. The net force on the dipole is 0. So it means it is fixed. If net force on the dipole is 0, it means dipole is not going to perform any kind of the translational motion. Why? Net force is 0. Net acceleration of the dipole, right, is 0. So I must say no translational motion of dipole. Whenever it is kept into the uniform electric field, no right, okay, no translational motion of the dipole is there. Torque with respect to the center, okay, with respect to the center, okay, just check it out, the net torque. This is a force. It is trying to rotate. If we are, right, grabbing this arrow and just trying to pull this up, the entire dipole is rotated into the clockwise direction. The same happens with respect to center. If we are trying to pull, right, the negative charge to this arrow, the entire dipole is trying to rotate into this clockwise direction. So it means that net torque is not 0. Okay, net torque is not 0. Right, net torque is not 0. So what happens here? If a net torque is not 0, then it would be, you can say I'm directly writing out, it is PE sine of theta, or that is P cross E. Okay, there is a small derivation, but we are directly accepting the formula, right? Net torque, force is equal to QE into the perpendicular distance, right? Like this way you can do what and reach up to the results, right? If this is L, then this is going to be L sine theta, right? Okay, like that way. Okay, so the most important results that we got when the dipole is kept into the, right, okay, uniform electric field, the net torque is not 0, but the net force is 0. It means what? The dipole is having the highest possibility to perform the rotational motion with respect to the specific point. Why? Net torque is not zero, and similarly it is having the zero possibility to perform the translational motion. It will not move into the rectilinear path. It will only rotate. Okay, it will only rotate. So whenever it is kept in an external magnetic field. So these are the important results. Okay, now what happens when the dipole is kept into the non-uniform electric field? We are going to discuss two cases into it. First, okay, just hold on, right? Some of the important part is remaining. Yes. Now, the formula of the torque, we saw it as PE sine of theta into unit vector n. Here, the equilibrium situation comes upon. Equilibrium situation comes upon. What does it states? Right? The angle between P and E will define everything. Angle between P and E will define everything. How? See, suppose if the direction of the electric field is like this way. Okay, let us take in some of our examples to understand this torque. Right? Electric field direction is like this way. Right? Again, I'm going to take three examples. Electric field is direction like this way. Okay, it is a uniform electric field. Electric field lines are parallel and then they're equidistant. Right? Suppose if the dipole is kept perpendicular, that we have seen into the beginning of the lecture meme, right? Angle between them is 90 degree, torque is maximum. Whenever the dipole, right, is kept, okay, into the direction of the electric field, this side we are having the negative charge, this side we are having the positive charge, right? Here it means that, okay, net force is getting zero. This situation, it is going to be stable equilibrium, right? Whenever the angle between, right, the magnet, this dipole moment and the electric field is zero, this situation is considered as the stable equilibrium, right? This situation is considered as this stable equilibrium in which the value of the torque is nothing else but zero. I'm sorry, not zero. Yes, yes, zero. I'm sorry, I thought it is a cos. Zero. Neither it is going to get rotate nor translate, situation of the stable equilibrium. And whenever, right, the dipole is kept, right, at 180 degree, whenever the theta is 180 degree, we are having the negative value, right? This situation, it is known as unstable equilibrium. Maximum torque when dipole is placed perpendicular to an electric field, right? Unstable equilibrium when dipole moment is anti-parallel, right, to the electric field. Stable equilibrium when dipole moment is parallel to the electric field. And see now here, everything is depending on only two factors, the net torque and net force. In this situation, both are getting zero. In this situation, right, any theta, at any theta, we saw that part, right? So in all of those cases, the net torque and net force is going to define everything. The net torque and the net force is going to define everything, right? Now, suppose if it is placed at some any angle theta, suppose this is in a direction of the electric field, right? This is the direction of the electric field, dipole is kept. Suppose here the net force is zero, that you all are aware of, because it is a uniform electric field, but net torque is not zero. Net torque is not 0. So what happens here? Dipole rotates. So whenever the dipole rotates in the external field, dipole rotates in external field, work is done. As this field is conservative, right? We have seen into the chapter of work, energy and power. Conservative forces, non-conservative forces. Conservative forces are having conservative fields. Non-conservative forces are having nothing. They are path independent. They are path dependent. So conservative forces, whenever the work is done in cases of the conservative forces, right, all of those time work done is stored into the form of potential energy. Here also the potential energy comes, that is PE, right? Generally it is PE cos of theta. You can define, okay, U as P dot E. But why I am not discussing this part? Because electrostatic potential energy, electrostatic potential, everything is going to come up within the 1 or 2 lectures, right? So here there is a possibility that whenever the dipole is kept, right, okay, whenever the dipole is kept, okay, it rotates, work is done, and that is stored into the form of the. Now, two most important results. What happens when the dipole is placed into the non-uniform electric field? Right? What happens when the dipole is placed into the non-uniform electric field? See, this is point A, this is point B. Okay, this is the direction of the electric field. Why I took all of those 3 examples? So that we can, right, we should be easily right, able to understand this concept. Sir, you told us non-uniform electric field. I gave you all an example. This is the non-uniform electric field. Why? Electric field lines are parallel and equidistant, but magnitude of electric field varies with distance. Right? Here we are having weaker field. This side we are having stronger field. This is the one of the examples, right, of the non-uniform electric field. Similarly, in this case also, this side, the direction is constant, but being a vector quantity, if the value is also getting changed, for a vector quantity to be constant, both magnitude and direction should remain same till end. But here direction is constant, the magnitude is varying or increasing with respect to x while moving from left to right. Similarly, weaker field here, and we are having the stronger one. Right, weaker field and the stronger field. Okay, so here this is a weaker one, this is a stronger one. Now here what happens? If the electric field lines are somewhat having different shapes, in this case when, okay, field lines are closer, electric field intensity is high. Electric field lines are away, less electric field intensity. So here this will be the stronger field, right, and this will be the weaker part. So this was a description regarding how the non-uniform electric field comes about. Now again, dipole is placed, everything depends on, right, everything depends on net force and net torque. Everything depends on net torque. Again I'm right, net torque, net force. In this case, both are non-zero. Both are not zero. Okay, in this case, both are not zero. Right, both of them are not zero. Why? Suppose if dipole is placed like this way, this is a negative charge and this is a positive charge. This is the direction of F1 force acting. This is the direction of F2. If I'm talking about the net force, then it is equivalent to F1 minus F2. Right? This is not 0. This is F1 minus F2. This is not 0. Why this is not 0? Because F1 will be greater than F2. F1 will be greater than F2. So in that case, what happened? Dipole moves into the stronger field area. Results. Dipole move towards stronger field area. Same when the dipole is kept reverse, right? Here we are having the negative charge, so force is F1. Here we are having the force of F2 is high. Sorry, force of again F1 is high. So in this case, the force of F1 is high. The dipole tends to move into the weaker field. Whenever the dipole is kept in this kind of the situation, right, nothing is fixed. It completely depends on the application into the non, right? It depends on the application, how field varies, how dipole is kept, in another sense orientation, right, and value of the calculation of net torque and net force. This will decide whether, see, in this case, dipole, whenever it is kept in the non-uniform electric field, there is a highest possibility that it will translate also and it will rotate also. But again, it depends on case to case things, right, how it is going to react into the non-uniform electric field. Okay, how it is going to react into the non-uniform electric field. So this was all about the electric dipole. Don't get worried. Again, this electric dipole, it is going to come into the electrostatic potential energies, right, and electrostatic potential. At that time, we are going to again revise all of those stuff. Okay, we are going to again revise all of those stuff. Okay. Now let's see some of the examples based on it. To infinitely, these are the examples generally based on the electrostatics. Two infinitely long parallel wires having the linear charge densities λ1 and λ2 respectively are placed at the r distance. The force per unit length of the wire will be what? This question is nice, so I kept it here. Wire 1, wire 2. One is having linear charge density λ1, one is having the linear charge density λ2. Force acting per unit length on the either wire. Can I name it as 1? Can I name it as 2? Force acting on 2 as because of 1. Force acting on 2 as because of 1 that we need to calculate. I told you all into the previous case. We are having the lots of examples in which directly we can apply the Coulomb's law. Directly superposition in principle is applicable. Everything can be done. But you'll always get confused when the two bodies are involved, two continuous bodies or two bodies having the uniform charge distribution or the varying charge distributions are involved, right? So what happens here? If we want to calculate the force per unit length of 1 as because of 2, on 2 as because of 1, then it is important to define, right, how much amount of the electric field that acts, QE, right? Okay, so force acting on 1 as because of, force acting on 2 as because of 1 is nothing else but charge on 1, right? Not charge on 1, okay, Q2, just hold on. Right now we are only defining it as Q and electric field, right? Q and electric field, right? Yes or no? Okay, so in this QE, this force acting, right, in this QE, this is always the electric field is of the source charge. electric field is of the source charge, right? Electric field is of the, okay, now how, at how much distance they are? Okay, they are kept at the distance of r meter, right? They are kept at the distance of r meter. Electric field is as because of the source, force is acting on the targeted charge. Okay, electric field is as because of the source, force is acting on the targeted charge. So simply I can define it as QE1, right? QE1. Okay, now force on second, can I replace it as lambda 2 into L, because lambda 2 that is equal to Q by L. Okay, E1 electric field as because of the wire, right, of this infinitely long parallel wire, right? Then we can say it as the electric field is because of the 1, that is 2k lambda 1 whole divided by r. This is force acting on 2 as because of 1. So here force we need to calculate force per unit length, so that is 2k okay 2k lambda 1 lambda 2 whole divided by r. This is the value of the force acting per unit length. Okay, second is the perfect answer for this specific question, right? Okay, so this is how it's, this is how the electric field plays a prior role into the, right? Okay, in this session the questions I have kept, those were nice, right? But it's okay, I'm keeping this session as much, right, sober as possible, because it is difficult to digest the dipole moment and all of those electric field into the uniform and non-uniform into the one take, right? So let's keep it simple. Okay, I'm going to give you all a small homework. This is based on the Coulomb's law, and the answer of this homework based question I want you all beneath the video. Don't get worried, the next question, the next session will be on to the practice based questions, and that time we are going to practice lots of questions from it. Okay, lots of questions from it. Okay, so but I think today right, we are going to keep that much only. Okay, so guys, I think it's time to go. This is a homework based question. We'll be waiting for all of your comments beneath the video. Okay, let's give you all another homework. Okay, another question is there. Okay, this is also homework from my side. Okay, I want everyone, each and everyone, to answer this question beneath the video, right? You can just have a screenshot for it. Okay, so guys, that's it for today. Okay, I will be waiting for all of your response beneath the video. Okay, in this chapter we have started with the Coulomb's law. We have completed superposition principle both in scalar and to the vector form. We saw some of the sums based on it, right? After we saw the electric field in the respective equations. We saw the dipole and everything. Now in this chapter, the Gauss law and some of the important stuff that is remaining. Electrostatic potential energy we are going to cover up into the next chapter, right? Okay guys, so I think it's time to go. This is Indrajit Singh signing off from the desk. Bye bye. Sat Sri Akal and Namaste from my side, Bachaji. I will be waiting for all of your comments beneath the video. Please do share. So this is Indrajit Singh signing off from the desk. Bye bye. Sat Sri Akal and Namaste from my side, Bachaji. Bye everyone. Stay at home, stay safe, stay healthy amidst this pandemic. Bye bacha.